In this video, I'm going to talk about different number systems, and then we'll proceed on how to do conversions between the different systems. Okay, so let's get started. The one that you're probably most familiar with is the decimal number system, and we all know how to just count sequentially. So if we look over here in the decimal column, you can see that we go 0, 1, up to 9, and then 10, so on and so forth. So I'm counting up to 31 in this example. Now, the important thing to notice is that in the decimal system is what's known as a base 10 system. And so we really only have 10 different numbers that we can use. We can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are the only 10 numbers that we have available in the decimal system. So how do we overcome that? Well, we overcome that in that when we get to our max number, which in this case is 9, then we roll over back to 0 and we increment the next column to the left. So I've counted from 0 to 9. I'm out of numbers, so now I'm going to increment or actually roll over back to 0, and then I'll increment my next column. And then we do the same thing. We count from 10 up to 19. At 9, I'm out of numbers. I've gone from 0 to 9, so I roll back over to 0, and then I increment my next column. Okay? And then when I get to 29, I roll over back to 0 here and increment from 2 to 3, and it just keeps going on and on like that. So that's how basic counting works, and so it doesn't really matter which system we're in. The decimal is a base 10 system, but we could also have, say, a binary system, and for binary, this is a base 2 system. And I really use these terms interchangeably. So, decimal is base 10, and so you may hear me say one or the other. I use these interchangeably. So binary is base 2. So we only got two numbers. We've got 0 and 1. Okay, that's it. So how do we count in binary? Well, we count the same way we do in decimal as we do in decimal. For binary, we start out at 0. Then we increment to 1, and now I'm out of numbers, because remember in binary I've only got two numbers, so I can't go up to 2. So 1 is my max number, so what I need to do next is roll over to 0 and increment this to 1. Now I'm at 1, 0. Well, I'm going to count up, so I'll go to 1, 1, but now this 1 is at its maximum, so I need to roll over to 0, and then I need to take this 1 and roll over to 0 and increment my third column. So this will take me to 4. Now at 4, I'm going to increment to 1 here on the rightmost bit. That's 5. And now I'm at my max bit, so I've got to roll over to 0, which means I increment this from 0 to 1. Then I increment from here. Now I'm at all 1s, and now when I increment, I'm going to have to roll over actually 3 times to get to this bit, to increment it to 1. Okay, so this may look a little, a little strange, but it's really operating the same way as we've seen in the decimal. Octal and hexadecimal are also common numbering systems. So octal is what's known as base 8. So you've got 0 through 7. Hexadecimal is base 16. You may hear this referred to as hex for shorthand. So we need 16 numbers. So we have 0 through 9, and that only gives us 10 numbers. So where do we get the other 6 numbers? We just start using letters. So we go A through F. Okay, so these are the different common types of numbering systems and the values that are allowed. So as you'll see here, Basically, in hexadecimal, we count from 0 up to 9, and then we go A through F, and F is our max value, so we roll over to 0, increment to 1. Count up from 1, 0 up to 1F, and then here we would roll over to 0 and increment to 2 for our next row. And octal is the same way. So octal, this is for base 8. You would just go from 0 to 7, and once you hit 7, then that's your max number. So you roll over to 0, increment to 1, count this up to 7, roll over to 0, increment to 2, count up to 2, 7, roll over to 0, increment to 3. Of course, this would go all the way up till you get to 7, 7. And once you get to 7, 7, then you would roll over twice and then increment to a 1 in the third column. Okay, so that's pretty much how that works. Is you're basically just counting up, and when you reach your max value, you roll over back to 0 and you increment the next column. And so, yeah, so that's how that works. So what I want to do now is transition over to talking about how to actually convert between the two, or between any of the four systems actually. So you don't want to just, in this case I've only got 32. You don't want to memorize a table, for all the conversions. You want to be able to say, hey, I want to, take this number 16 that's given to me in decimal, and how do I convert that to binary, which turns out to be 1 0 0 0 0 in binary. So how do we do these computations? And so that's what I want to discuss next. And so I've broken this up into four. You basically have four categories. You have the category where you're starting with a decimal number. So you're going to start with a decimal number, and you can convert to either binary, octal, or hexadecimal. Okay. The second group I have is basically going the other direction. So the second group, what you want to do is start with either binary, octal, or hexadecimal and go to decimal. So this way you're going in reverse direction. Okay. The third group is going to be when you're going from either binary to octal or hexadecimal, or octal or hexadecimal to binary. That's what I call bit grouping. And the fourth group category is when you're going between octal and hexadecimal. Okay, so these are the four categories of different ways to do the conversions. So let's just start with let's start at number 1. So let's start with a decimal number. So we just pick any decimal number, and we can convert to, say, binary, octal, or hexadecimal. Okay, and so what I've done is I've given you 12 examples here of how to do these conversions. So when you're starting with a decimal number, when you're starting with a base 10 number, which is decimal, you do what's called successive division by the base of the destination number. Okay, stop when 0 is reached and the answer is displayed in reverse order. So this is a very, very simple algorithm, and that will give you your desired answer. So let's I think it's good to look at examples. So let's look at this example 1, where I have the number 115. Now the subscript 10 is indicating base 10. So I didn't show that over here. Actually, for decimal base 10, if you put a subscript 10 beside a number, that also indicates what base it is. Okay? And so here we're going to start with 115, which is in base 10. And in this instance, I want to transition to binary. Well, binary is base 2. So what does the algorithm say? It says, well, I'm starting with a base 10 number, which is 115. So that's in base 10. Now I want to perform successive division by the base of the destination number. Well, the destination number is binary, so it's base 2. So that means I'm going to be successively dividing by 2. And I'm going to stop when I reach 0. And my answer will be in reverse order. So let's look at this example. So I've got 115. So here's the division, 115 divided by 2. Okay, that's going to give me 57 with a remainder of 1. And then as you keep going through, 57 divided by 2 will give me 28 with a remainder of 1. 28 divided by 2 will give me 14 with a remainder of 0. Okay, and then I get down here, 1 divided by 2 gives me 0 with a remainder of 1. And once I reach 0, that's where the algorithm ends. Okay, and so my answer is going to be in reverse order. So I'm not going to read my answer top to bottom, it's going to go bottom to top. So that says that 115 binary, or I'm sorry, 115 decimal, base 10, is going to be 1110011. So 1110011. Okay, so that's the binary equivalent of that decimal number. Now, there's really no significance to the spacing here. What I like to do is, in longer numbers, especially binary, is just write them in groups of 4. Just makes it a little easier to read. So anyway, I mean, there's no significance to the spacing. It's just really for readability. And that's our answer. So let's verify that. So if you have, say, a Windows calculator, there's a programmer, and let's go to decimal, 115 decimal, and binary is 111 and 0011. Okay, so that is correct. So that's the right answer. Now I've also written a C program that will also do some of these conversions. So if I want to do, this is what, decimal to binary. Okay, if I want to do decimal to binary, then I can run my program, and decimal to binary is option 0. So you enter a base 10 number, and what was it, 115, 115. So that gives me binary value 1110011. That's 1110011. So that's good. My calculations and my program and Windows program, they all concur. Quit that. Okay, so the other ones are going to be the same. It's just you're going to change the base number you're dividing by. One other thing I want to point out here is the remainder. Now with binary numbers, it's not too bad because it's only going to be 0 or 1. But when we get into other bases, you can have remainders that are, more than just those two options. And so what I said here is, this becomes much more useful when converting to octal and hexadecimal, since there are more than 2 options for the remainder. So here's the way to think about it, and I've written it here, and hopefully this makes sense here. But basically what you do is if you have 115 divided by 2, okay, so if we go here, okay, now if I do say 115 divided by 2, well, that 57.5, I mean, that's 57 and a half, so that's going to be 57 remainder of 1. But what you can do is just take the 57, okay, so just take the 57 and multiply by 2. And that gives you 114. And how far away is 114 from 115? Well, that's a difference of 1. So that's your remainder. Okay? And so that's what I've said here. So one way to compute the remainder is to take the quotient value, in this case it's 57, and multiply by the base, so 57 times 2, and then subtract that number from the previous value in the division column. Okay, so 57 multiplied by a base of 2 is 114, and then 115 minus 114 is equal to 1. Okay, so that's how you can calculate the remainder. And like I said, for binary, it's not too bad, because if you see 0.5, when you do the division, you do 115 divided by 2, and you see 0.5, you know it's a remainder of 1. If you get a whole number, you know it's a remainder of 0. Okay, but for the other two systems, there's more options for the remainder. So this is where it'll come in useful. All right, so let's move on to example 2. Okay, so this time I've chosen a different base 10 number. This is 2619, and we will go to octal. Well, octal is base 8. Okay, so we're going to go from decimal to octal. Okay, well, it's the same algorithm. So we take our number, 2619. This time we're not dividing by 2, we're dividing by 8, because we're going to the octal number system. And this is where this will become more apparent with what I was just talking about with calculating the remainder. So let's do 2619 divided by 8. So we've got 2619 divided by 8. Well, that's 327. So we've got 327. That's going to be my quotient. Now, what's this 0.375? Well, I mean, what's that in terms of the remainder? Is it a remainder of, well, it's clearly not a remainder of 0, but, it may not be, completely apparent what the right answer is. So the easy thing to do here is to take the 327, multiply by 8. That gives me 2616. 2616 and 2619, that's a difference of 3. So my remainder is 3. Okay? Then we take the 327 and we divide by 8. So let's do 327 divided by 8. 40.875, so it gives me a 40. That's my new quotient, is 40. Well, how do I figure out that I get a remainder of 7? How do I know 0.875 is a remainder of 7? Well, I'll just do 40 times 8 is 320, and 320 is 7 away from 327. So that's a remainder of 7. And again, once you reach 0, that's when you stop. Okay? And so 2619 base 10 is going to be 5073, 5073 base 8. Okay? And again, you can check this. So if I use my program, okay, I'm going to do option 1. We'll do base 10, which was what, 2619, and we will go to octal. It's 5 and then 073. Again, the spacing is not really significant. It's just more for readability. So 5073 and 5073. Okay, so that's the octal. Well, what about hexadecimal? Hexadecimal is going to have 16 numbers. Okay, and so once you get to 10, from 10 to 15, you need to use A through F. All right, so let's look at hexadecimal. Right, so for hexadecimal, we're going to start with the number 25144. And again, I mean, we're dividing by the base that we're going to, so now we're dividing by 16. We're not dividing by 8. We're not dividing by 2. We want to divide by 16. We do the same thing. And again, to calculate the remainder, right, if you use your calculator, we've got 25144 divided by 16 gives me 1571. Okay, 1571. Well, what's the 0.5? Well, if I take 1571 times 16, I get 25,136, which is 25,144. That's a difference of 8. So my remainder is 8. Okay, and so once we do that, we do 25144 base 10 is equal to 6238 base 16. Right? So if I do base 10, so 25144, okay, I get 6238 in hexadecimal. 6238 hexadecimal. And you can see the subscript 16 for hexadecimal. So the important note here is that if you get a remainder between 10 and 15, in this case I did not, but if you happen to get a remainder between 10 and 15, then that's going to map to A through F. So for instance, a remainder of 13 would correspond to the hex value D. So you would actually have a remainder. Your remainder could be A through F as well. Okay, so that's how we do when we're going from a decimal number. We want to go to one of the other 3 bases. We do what's called successive division. And so that's what I've shown here with these examples. All right, how about the other way? Well, the other way is actually, I guess you could argue it's even more simple than that, because when you're going from binary, octal, and hexadecimal to decimal, you just do what's called expansion. And it's very straightforward. So when you're starting with base 2, 8, or 16, you want to do expansion. So beginning with the most significant digit, which is the left side, just like if you're reading a number, the leftmost digit's the most significant. You're going to take each digit, multiply by the base of the number raised to the column weight. Column weights begin at 0, starting with the rightmost digit. So this rightmost column is weighted 0, 1, 2, 3, 4, 5, 6, 7. So these are weighted 0 through 7. And then sum up all the values to get the decimal value. Okay, so let's look at examples 4, 5, and 6. Well, example 4 is a binary number. So it is a base 2 number. I go from column 0 up to column 7. So I take 1, I take the digit, okay, so beginning with the most significant digit, so I take the digit, which is a 1, multiply by the base of the number, which is 2, raised to the column weight, which is 7. So this will be 1 times 2 to the 7th, plus 0 times 2 to the 6th, plus 1 times 2 to the 5th, plus 1 times 2 to the 4th, plus 0 times 2 to the 3rd, plus 1 times 2 squared, plus 1 times 2 to the 1, plus 1 times 2 to the 0. And just remember, any number raised to the 0 power is always 1. So when I compute these intermediate values, then sum them up, then I get 183 base 10. And you just do the same thing for octal or hex. The only difference is you replace the base. Instead of using 2 for your base number, you use 8 or you use 16. And of course, with hex, these numbers can get very large quickly. but that's essentially it. I mean, you're reading a number from left to right and multiplying, taking each digit in order, multiply it by the base raised to the power of the column weight. And again, all the columns, they start on the right at column weight 0, and they go all the way up till the end of the number. So this one goes 0, 1, 2, 3. This has column 4, and this has column 7 again. Now, the other thing to keep in mind is that 8 columns doesn't mean the left column is weight 8. It's everything starts at 0. So you go 0 through 7. So keep that in mind. So yeah, this expansion method is pretty straightforward. All right, now what about and again here, like in this instance, I have an A. So I mean I replace that with 10. When I have C, I replace that with 12. And then F I replace with 15, and E I replace with 14 when I'm actually doing the numeric computations. Okay, so what about the third category? Well, this is when you're going from binary to octal or hexadecimal, or when you're going from octal or hexadecimal to binary. And this is what I call bit grouping. Tried to kind of explain it in words, but examples I think are usually more beneficial. So when we starting with a base 2 number, we're going to convert to octal or hexadecimal. Perform bit grouping. So use groups of 3 binary digits for octal and 4 binary digits for hexadecimal. And so simply convert a grouping of 3 to octal with possible values 0 to 7, and 4 grouping of 4 to hexadecimal with possible values 0 to F. Progress from right to left. So let's look at an example. Okay, so let's look at example 7. So here I want to go from binary, got a 12-bit binary number. I want to go to octal, which is base 8. Well, base 8 means I need groups of 3. Okay, so I start here. If you look, this rightmost group of 3 bits here, maybe let's see if I can zoom in a little bit. Yeah, I think that's better. So if you look at these 3 bits right here, well, 111 corresponds to 7. Okay. If you go back to this table, okay, then basically a binary 111 corresponds to octal 7. Okay, and it's actually pretty useful to just kind of memorize just the first 16 from 0 to 15, because you want to be able to convert quickly from binary to hex or binary to octal, and so if you see 1010, then you should be able to know that's going to convert to A, hexadecimal A. Okay, all right. So here 111 corresponds to 7. Then we go to the next group of 3, which is this group. Oops. Okay, there. So I did this rightmost group of 3. 111 corresponds to 7. What's 001 correspond to? Well, that corresponds to 1. Okay. My next grouping will be oops. Well, it's having trouble highlighting what I want, but the next grouping is going to be 011. 011 corresponds to 3, and that just leaves me with 101, which corresponds to 5. Okay, and so this number 101011001111 corresponds to 5317. And in this one, I picked the same number here in binary to go to hexadecimal. So the only difference is we're grouping 4 now. So here, 1111 corresponds to F, 1100 corresponds to C, and 101010 corresponds to A. So this same number, the same binary number, equals 5317 in octal and ACF in hexadecimal. Okay, and then let's see, going from octal or hexadecimal to binary, we also do bit grouping. So let's look at example 9. So this is an octal number, and at this point we just read off like 3 is 011, 7 is 111, 1 is 001, 2 is 010, 5 is 101. Okay, and so we just write it out just like that, and I left off the leading 0 here. Okay, so this would be 11, 111, 001, 010, 101. And then the same thing going from hexadecimal to binary, you just basically replace each hex digit with its 4-digit binary number, or 4-bit binary number. So here we have 94CA, 10FF. Just write off the write its binary representation, and again here it is. Okay. Now the last category is going in between octal and hex, and I just recommend going through the binary intermediate step. So if you're converting, say you want to go between base 8 and 16, well, here's a base 8 number. I would just do the bit grouping. So 31202, 31202. This would be the binary representation. And then and then convert this number to base 16 using the bit grouping as well. But remember, when you're going to base 16, you're doing groups of 4, okay? And so you got to be careful here and do this group of 4. So 0010 would be 2, okay? And then you just go group of 4. So after 0010, you'd have 1000. So that would be 8. Then you would have 0010, which is 2. And then you would just have 11, which is 3. And then same thing for going from base 16 to octal. Convert your base 16 number to binary just by writing out, the bits that correspond to that hex digit. Now you've got it in binary, and now you convert this to base 8 using bit groupings, but now you're doing groups of 3. Okay, so you have 001, which is 1, 111, which is 7. Okay, and so you would end up with 122671 in octal. Okay, in octal. Okay, let's zoom down a little. back to normal. Okay. Okay, that was a lot of information, but I want to bring this video to a close. I hope you found this useful in understanding, um, the different number systems. So decimal, binary, octal, hexadecimal. You could have other ones. You could have a base 5 system with numbers from 0 to 4. You could have a base 3, a base 6 system, but these are the most common. And then for doing the conversions, I would say probably going between octal and hex um, is the least common. Um, the the ones that you'll probably find more useful are um, you know category 1 going from decimal to binary, octal, hex, and category 2 binary, octal, and hexadecimal to decimal. Um, and also category 3 to some extent as well. But so I guess, I would, um, all 4 are important, but maybe just if focus on the first 3 uh, different categories. Okay, I'm going to end the video now, and I hope this has been helpful and that you've learned something.